Perez, as my colleague Richard said, and my talk is going to be divided into three sections. It's going to be divided into, first part, an explanation on multiband observations. Second part is going to be over a dissertation in which a researcher did multiband observations on the planetary systems WASP-48 and the planetary system HAT-P-23. So we're going to be looking at that, and then the third is going to be, towards the end, very briefly, we're going to be talking about spectroscopy and how multiband observation leads into spectroscopy.
You know, the guys that are connected to Zoom probably should mute, please. If you mute, it's going to help. Just hit the mute button on your mics and that should help.
Okay, so for the beginning, I'm just going to go over a couple keywords or phrases, just a couple words I either know while learning about this and maybe some of you as a refresher. So the first one's obviously going to be multiband observations, and now I'm going to touch on that a lot more. Second one's going to be radial velocity. So the radial velocity is the velocity of an object along the line of sight of an observer. A dichroic filter, which is a thin filter used to selectively allow certain wavelengths of light to pass through. The other wavelengths that are not selected will be reflected. So that way the only light that goes through the filter is the light that we want, which is going to be very useful for both multi-band observations, and the physics behind it is going to be very useful for spectroscopy. We have limb darkening, which is a phenomenon that makes the edges of stars to seem dimmer than the center, and the reason for that is because whenever you're looking at the edge of a star, specifically I could use the sun as an example, you're looking at the thicker part of the atmosphere, which causes it to look a little bit dimmer than if you're looking at the center, which is the thinnest part. Then spectroscopy, which is the investigation and measurement of spectra produced by emission of electromagnetic radiation being light. And then Monte Carlo algorithm, which are randomized algorithms that have a small probability of being incorrect. That's going to be used just for the uncertainty for the research that was being done in the second part of my talk. So what is multiband observations? Well, multiband observation is the photometric observational technique that allows for observers to gather light curves in different wavelengths. Not to be confused with spectroscopy, which is a different area of optics altogether. However, this still uses filters to allow only certain wavelengths to project it onto the CCD at a time. So basically, we're still looking at a photometric light source being inputted in from the stellar object that we're looking at. And what we're doing is we're just looking at it in different filters. So we can be looking at it in the red wavelength, we can be using the visual wavelength, in the blue, and the infrared. So that is basically the whole premise behind multi-band observational techniques. So the process of multi-band observation. So this is a very nice image given to us by Richard, given to me by Richard, so I can put here. It looks really nice, and it's just kind of like a night sky, and what kind of planning these dots simplify what kind of planning is being done for an observation. So for the planning of the multi-band time series, first we need to choose a target. So when we're looking at the target, we need to find, okay, how fast is the transit? What kind of sky conditions are there, and what kind of planet it is? That way we know where in the sky it's going to be, how long do we have, the time window that we're going to need to take, because some transits can be very fast, so a couple of hours to maybe half a day. So we need to make sure that we understand how long we're going to be taking. The second thing is an observational parameter, which is the transit time, so the beginning, center, and end transit. So the beginning, center, and end transit basically just means that as soon as the planet or the object going in front of the star begins to go in front, and then the center, and then the end. That's pretty intuitive. We need to put the sky position as a function of time. That way we understand where everything's going to be whenever we're there at that point in time. Now we need to have our photometry strategy. The filter set, what kind of filters we're going to be using for looking at this, and that's all going to depend on what kind of techniques you're going to be looking for. We have the cadence, which is, okay, how often are we going to be looking at this in terms of the shutter time, and then we have our duration, how long are we going to be doing this for, and the reference stars. So the reference stars are very important because you need something, you want to have kind of like an idea before you actually start observing as to what you're looking for, and the way you're going to do that is by using a reference star. Now, in continuation of that, we have the observations. So we have the reduced, we have the bias, flat, and dark reductions, which are basically just correcting the images. We have the alignment, and we have the time series differential photometry, which is actually plotting the measurements and calculating the magnitude with respect to your reference star. So that's why everything is important. This is pretty much the culmination. This is where you get all of your data from, and you use this to extract everything that you're pretty much looking for or hope to get. Objects targeted by multi-band observations. We have exoplanets, which is what I'm going to be focusing on today, but other objects can be binary star systems, asteroids, or solar flares and blazars. Blazars, in case nobody knows, or some of you may not know, they're feeding supermassive black holes that produce a high-energy jet face-on from Earth. They're pretty cool. They are a part of the group of objects called active galactite nuclei. And so all of these and other kind of minor stellar objects can be used as targets for multi-band observation. Now, why do we want to use multi-band observation? Well, there's a very good reason for that. So, multi-band observation allows for a much more accurate measurement of physical properties. This is because we're looking at things through different wavelengths, and because we're able to get the light curves and understand everything that's going on with that planet to a certain degree, it allows for a lot better than if we're just getting all the light coming in, kind of like the white light that would be from a standard photometric observation. The physical properties help deduce information about formation, age, and atmospheric composition of exoplanets. So the physical properties can be deduced from the wavelengths and the light curves that we get, and I'll have an example of that later on in my talk. And they allow for a much more deeper understanding about the formation of planets and their different possibilities, like the populational and the population of different planets, which is going to help in the future for further astronomical projects. Does anybody have any questions so far? I know might be going a little fast, but I'm just a little nervous, not gonna lie. No questions? Okay, great. So so before I talk about exoplanets, we are here at the Center of Gravitational Waves Astronomy. So I found a really interesting article that I can provide the link for at the very end. And it's basically just multi-band observations of gravitational waves. So the gravitational wave system. This was done by a Japanese gravitational wave research team, DESIGO, which is Decihertz Laser Interferometer Gravitational Wave Observatory. That's kind of a mouthful. Research team used multi-band observational techniques. Their band slots were between the hectohertz region and the millihertz region. And they did this for systems like GW170817. And they were able to measure the mass ratio to less than 0.1% off, individual black hole spins less than 10%, and coalescence time of less than 5 seconds. So they were able to get a fairly accurate measurement by doing multi-band observations. And this is going to be one of the arguments I'm going to have for why multi-band observations are very important to astronomy. So I just wanted to touch on this really quickly, just because I know that most people here are interested in gravitational waves. So now we're going to get to the second part of my talk, the multi-band observations of HAT-P23 and WASP-48 planetary systems. The purpose of this dissertation was an optical follow-up of planetary systems. The goal was to deduce the physical properties using multi-band observations, and the techniques used were photometric observation techniques, namely multi-band observations. So here, I know it might be kind of blurry, but this is a nice little neat chart I found, which you have the planet radius here, and you have marked the separation in astronomical units from their solar star. So right here are the two planets. I believe this one is WASP-48, and this one is HAT-P23. And this, just to give you an idea of where they are, I know it might be a little bit blurry, but this goes up to 2. The radii, the temperature goes up to, I believe, 3,000 Kelvin, and here it's 0.3 separation in astronomical units. I believe it's 0.3. So,
Can I ask you something
yes.
about that plot? So, when you say the planet radius goes up to 2, is in terms of some, I mean, what is 1?
Yes,
In that unit?
so the planet radius is in terms of Jupiter.
Oh, okay,
Jupiter
in terms of
masses.
Jupiter. Okay, so 1 is the radius of Jupiter.
Yes.
Okay. And now, these are only the planets.
These are exoplanets. These are exoplanets that are transit around a star.
And how many of them are?
It doesn't say in the graph, but you can tell here there's a fair amount. I want to say, to be honest, I'm not 100% sure about how many there are located in this graph.
Okay, all right. But they belong to different host stars.
Yes.
The whole time, yeah, obviously they're not a star that has that many planets, but so there are many.
Yes. So
And one more question, sorry, but this is a very interesting plot.
Okay.
So the separation in astronomical units is of the exoplanet equation to the host star.
yes.
Okay.
So it's very small. So I believe this is not all known exoplanets, just because I know that the WASP 48b and HAT P23b are actually very close to their host star. In terms of
this is so annoying. I have one more
Oh, it's
question.
okay, it's okay.
The temperature is the temperature of what?
Yes, it's the equilibrium temperature, the accepted value of the equilibrium temperature of the planet itself.
Of the planet itself.
Yes, so would those be hot Jupiters? Because they're hot, they're big, and they're close to the star.
I am not 100% sure whether they are hot Jupiters. I might mention it later on in my talk. I believe I have a chart that might answer your question on that. Okay. Any other questions?
No. Thank you.
So I'm going to talk a little about WASP 48, the planetary system. So here we have WASP 48, and we have right here just above 0.2 astronomical units, we have WASP 48b. WASP 48 is an F-type star. It has a solar mass of 1.19 solar masses, and one planet orbiting WASP 48b, which has 0.98 Jupiter masses. So just slightly under 1. And then HAT P23. HAT P23 is a G-type star. Usually, I believe those are classified as yellow dwarfs. 1.13 solar masses. One planet orbiting, HAT P23b. The mass of HAT P23b is going to be 2.09 Jupiter. So this is going to be considerably larger than the exoplanet found in the WASP system. So, the observations that the researcher did, they did 8 transit events were recorded for HAT P23 and 7 transit events were recorded for WASP 48. Both systems were observed using a multi-band imaging camera, the DLR MK3. One transit event was observed using the Bonn University simultaneous camera. Something very interesting about this camera is that they were able to observe the planet, the transit object, at 4 different bands at the same time. However, there was an issue, and I'm not sure if this is a chronic issue, where they were facing oversaturation at the R wavelength. So they cut things off right when it became oversaturated at the R wavelength. So all the other wavelengths were a little bit, they weren't as strong as the R one. But that's the way they had to do it, because if they kept going with the observation, their data would have gotten a little bit messed up.
Do you know the telescopes they use for this?
The telescope, I am not 100% sure. I can find it though. It's on the paper. From my understanding is that they used 2 different telescopes. So I'll get back to you on that. And then the data reduction was performed using the standard methods that they talk about, standard like photometry methods. So now, just a quick, these are the observations. So, here we go. This is the telescope. The CA, just a quick note, all of these telescopes are pretty small. The largest one is a 2.2 meter. So you have the telescope here, you have the Cassini, and you have the CA. I forgot exactly what the CA stood for. You have the dates of the observatory, the start time, the end time. You have the filters, and for some reason they didn't explain why in the paper. They use different filters. However, I don't believe it's because they want to get the different wavelengths, because you have Thuan Guan, I believe that's U, and then G, and then R, and then Z. I'm not sure why. But all of these up here are cousins R, and then you have cousins I, they use cousins R again. I'm not 100% sure on why they use those kinds of filters. There could be an underlying reason, but it wasn't expressed in the paper. So now we have the light curves. We're going to talk about the light curves that we got from these observations. So the fits of the light curves gathered were performed using theoretical values of the Lin darkening coefficients while fitting the linear coefficients to the curve. So and the quadratic coefficients were fixed during this process, yet were altered during the uncertainty part of the paper. And I'll get to that in a little bit. But basically, this is just saying that they got all their equations and they got the linear coefficients, and that's what they used to fit the line of a curve, like the line regression, to be able to get an accurate light curve of what they were looking at, whether it was WASP 48 or HAT P23. So these are the light curves that they got. This is HAT P23, HAT P23, WASP 48, and WASP 48. These are from different telescopes. Now, right here, you might notice that on here they have the curve. There's like a little deviation here in most of these. This one's a little bit larger. But right here they have straight lines, and this is what's known as a residual. So basically, this is the data subtracted from the model, and this is where you get your residual curve, which is basically what you're kind of looking for while doing these kinds of observations. I know that the gas might look a little muddied. My apologies. But basically, these are the light curves that they gathered from the 7 and 8 transients, and I believe that this is like the mean. They have the observational date right here, right next to the light curves that they got. So, just as an indication of when and where these light curves took place. Now, the physical properties, which is something that is probably the most interesting part of multiband observations, the deduction of them. So the physical properties were deduced by taking the data gathered by the observations, interpolating them with stellar models, and finding the best fit. And this is where the Monte Carlo algorithms come in. So the Monte Carlo algorithms, basically they were stellar models that came in and they fed data to them, and they kind of ran, I believe, upwards to approximately 1,000 algorithm tests to get a mean for the data that should be given than the data that they already had. So here it might be kind of small, but these are the telescopes again, and you have your radius A and your radius B. The radius A being the radius of the star, radius B being the radius of the planet. Your K being the RA over RB. I'm sorry, the RB over RA. You have your excuse me. I is going to be your the incident M. The exact words for it. Inclination, your angle of inclination, which is basically kind of like the tilt of its axis. And then here you have your separate for RA and RB, which is basically just their radius. So what I found out is that for here, and this is going to be interesting in a little bit, that they go strictly for the radius and then they calculate the mass. And that's going to be interesting in a short while during the third part of my talk. So the final results of their physical properties. So here's the physical properties for the HAT P23 system. You have your mass. You have your mass of your star, the radius of the star, the surface gravity of the star, surface density, and then you have the same values for your planet. Same thing over here. Now, what I really liked about this researcher and the paper that they wrote was that they got the same values, not the same values, but they got the values for these variables from the original discovery paper of these systems. And these were, I believe, using just regular photometric observations, and this is the data that they acquired from multiband observations. And you can tell, and I'll talk about a little bit more, that these are a lot more concise and a little bit less of a larger estimate than the actual photometric observations. So that's something I'm going to be talking about in a little bit. So the data analysis. So HAT P23b, from the HAT P23 system, the mass was equal to the original, yet the radius was smaller by roughly 1.5 sigma, which means that the density was a lot higher than the original discoverer had predicted. And then in the WASP-48 system, it turns out that the estimates for the mass and radii were a lot smaller than the original discovery paper. The stellar radius was smaller by a factor of 2.2 sigma, and the planetary radius was smaller by a factor of 2.4 sigma. So this basically meant that the original discoverer, because this paper I believe was written in about 2015, the original discoverer 4 years prior had a lot larger estimates for these numbers. So this is something that's very interesting to me because it shows that the more optical follow-ups that you do, the more refined your data can become. So this is another interesting. So this is a chart. This is the mass versus radius diagram of transiting planets. The blue and red dots represent the values for HAT P23, the blue and red right here, and the WASP-48 found in literature and obtained in this work. So, sorry, the blue is where they were in the literature and where they were in the actual discovery. The red is where the multi-band observational technique put them at. So you can see that there's quite a bit of shift, especially in the WASP section. So it turns out that these were actually a lot closer to this like nice little corner here than these were. These were kind of outlining the outer regions, especially HAT P23. Yes.
Can I actually point out something interesting?
Yes, go ahead.
The error bars in radius and in mass. The mass error bars stay the same, but then the radius estimates improve. So is that consistent with what, like, because they're doing photometry, right? Mm-hmm. So is that what would we expect? Like, why are the mass error bars not changing?
The mass error bars not changing?
Yeah.
I'm not sure I would be able to give you like an actual in-depth explanation to that.
so I almost not changing.
I mean, what I think is because they're doing photometry, so transits are to get the radius, and then spectroscopy is how you do the Doppler shift and get mass, so they probably didn't improve the mass estimate.
Yeah, so that's going to be very important in my talk later on when I start talking about spectroscopy and how you can just but it would be actually a lot easier to find the mass. So here, as I said before, they're actually going for the radius instead of to calculate the mass. However, in spectroscopy, we go for the mass first.
So you get the total mass for the system.
Yeah, the total.
Then you have to remove from a model the mass of the star.
Yes. Yeah.
And that didn't change with the
Yeah.
multiband photometry.
Yeah.
So I think that is the reason.
Are there any other questions? Okay. So now for the conclusions of the paper, following up on exoplanets and other celestial objects is a very important part of astronomy. Using new techniques, in this case multiband observations, has allowed for better approximations of physical parameters. The results of this paper show that the estimates of WASP-48 and HAT-P23 planetary systems can be refined further. And I hope in a couple years I might be able to do an observation on WASP-48 and HAT-P23 and see if I can refine them even further. Refining information will allow for better approximations for algorithms and models used for other astronomical projects and better population statistics. That's basically the whole goal. Especially for me, what I want to do is I want to be able to create data that's going to help other people with their own projects. So this was a very good point, both in the conclusion and in my own head. I believe that this was probably the most impactful thing from the paper. Now, for the third part of my talk, I'm going to be talking about spectroscopy. So multiband observations is a step into spectroscopy. Spectroscopy is the science of splitting light into a spectrum to observe the lines of emission/absorption. Lines of emission or absorption is the line on the spectra that corresponds to the unique wavelength observed through spectroscopy. So here we have a very basic spectroscopy setup. You have a light source coming in and you have a prism. This was one of the earliest depictions of a spectroscopy. And then you have the light being diffracted through the prism. And then you have your gradient right here, which is going to give you your lines right here. So you can do this, and most people did this with like common lights to find out what kind of gas. So you could have a bulb filled with helium, and if you heat that up, if you excite the particles, you'd be able to see a very specific lines of emission from the bulb of helium coming through. So this is the basis for spectroscopy. This is basically the physics behind it, without the equations. So now spectroscopy in the modern era. This is where it gets a lot more interesting for me. Spectroscopy has changed since its first scientific debut. Diffraction gratings are now used to disperse the light observed, which then goes projected onto the CCD. This allows for more complex spectroscopy to be done. So here is one of the earliest. This is basically the principle behind spectroscopy. And then you have now the much more complicated, which the light comes in from the star, hits the mirror, it hits this plane. It goes onto here, and then you have another mirror, and then it goes to the diffractor, and then you have the computer reading all the signals. So basically, this is just a fancy version of this, because you're not getting as much light source as you would from if you were holding a prism to the sun. So you need to focus it, and you need to make sure everything's going to be okay for your data to come through nice and sharply. So now spectroscopy on exoplanets. Spectroscopy on exoplanets is different from multiband observations of exoplanets. Instead of looking at an exoplanet through different filters of a photometric observation, the lines of emission from the planet's electromagnetic radiation, aka light, are observed. This allows for a better understanding of atmospheric and planetary composition and formation. And I'll talk a little bit more about that right now. So the benefits to astronomers. Spectroscopy helps unlock many physical parameters from celestial objects, such as the mass. So the way that we can calculate the mass is if we're looking at a spectrograph from a light source coming in from a stellar object, and then if we see it and we get it from the light source, and then if it's transient and it's going, there's going to be a very small moment. There's going to be a very small moment where, as it's transiting, you have the star here and you have the exoplanet here. As it's transiting, there's going to be a very small window where the atmospheres overlap from each other. When the atmospheres overlap from each other, you're going to get your lines of absorption, which is basically, and then from there, you see the lines of absorption, and then you can subtract it from your image, and then you get your shifts. And then, as the planet is transiting, the star also begins to wobble because of the slight gravitational pull from the star. So as it goes around, you get you get your different lines of emission, but some are going to be shifted. So you get your most Y shift from there using the equations. I don't want to like really get into the specifics of it, but you find your delta lambda, you get your delta V, and then you go further into it, and then once you calculate everything, that pretty much gives you the mass from the shift in spectral lines because of the difference in overlapping atmospheres. So that's how you get the mass from spectroscopy, which to me is a lot more interesting because with mass, it's a much more direct way of finding it other than multi-band observations. And then much better atmospheric understanding because you get to read the spectrum from the stars, transit begins, planetary atmosphere overlaps other atmosphere, and you get the same spectrum with absorption, which is basically what I had said earlier. But this is basically because you're not looking at different wavelengths of light. You're looking at the actual spectra coming in from that light. So if there's an abundance in a certain gas or a certain metal, you're going to be able to deduce that a lot quicker due to the lines of emission and the lines of absorption. So you're going to get certain bars here that are going to tell you, okay, well, if you know that you have 4 lines in the red spectrum and you have 2 lines in the violet spectra, that's going to give you X element, and that's going to help you understand the atmospheric composition, which is great because with exoplanets, at least what I'm looking for is planets that can sustain life, and one of the most important things is its atmospheric composition. So this is a very basic spectrograph that you get, the data reading from one, and this can be obtained from getting a spectrograph and looking at a light source coming in, maybe the light source in your room. And this is going to be one a little bit more complicated that's going to be coming in. And this is actually spectra from the S7 spiral galaxy. So you can see here how you have your emission lines right here, and then you have your lines of absorption. And these are going to correlate with this. So that's pretty much how you get it. So you see this huge spike here at the 650 nanometer wavelength. That's going to correspond with one of these spikes right here. So that's basically how you translate the original physics from the spectroscopy to astronomical spectroscopy. So that's pretty much it for this part. And I believe that is all for my talk. Thank you to Richard Camacho for answering any and all questions I had making this presentation. And special thanks to Dr. Maria Diaz for allowing me to give this talk.